In this video, we're going to talk about section 5.1, which goes over randomness, probability, and simulation. The first I can statement is I can interpret probability as a long-run relative frequency. We're going to define probability with the textbook, and it's a little bit different than what you've learned before in previous classes like Algebra 2. So in this case, the probability of any outcome of a chance process is a number between 0 and 1. This is something that's review. Second half of the statement is different. That describes the proportion of times the outcome would occur in a very long series of repetitions. So you've been taught previously that it's a simple fraction, the number of desired outcomes over the number of possible outcomes. This talks about if you repeat the same event for a very long number or very large number of times, it approaches some proportion. Okay. So this is a another way of saying chance behavior is unpredictable in the short term. But predictable long term. The law of large numbers says if we observe more and more repetitions, of any chance process, the proportion of times that outcome occurs approaches a single value. And that single value is what you usually have found in a fraction in between 0 and 1. So flipping a coin was 0.5, for example. Rolling a die and getting a 3 would be 1 out of 6. Those are the numbers it would approach, that proportion. You guys have learned probability as the number of desired outcomes over number of possible outcomes. So as I said before, for example, the probability of rolling a 3. There are 6 sides to a die. There's only 1 3 on the die. Your probability is 1/6 or 1 over 6, and or percentage is like 16.7%. It doesn't mention long term in that definition. And in actuality, in the short term, that probability experimentally could be very varied. It wouldn't necessarily be 1/6. It could be very unpredictable in the short term. But what this is saying is that long term, if you do enough flips, it'll be that 1/6 number, or approximately 16.7% long term. An illustration of that is these two graphs. The two diagrams display the proportion of heads after 20 flips of a coin and then 500 flips of a coin. So proportion of heads starts off at 1. That's 1 flip, 1 head. 2 flips, 0.5. That's 1 head, then 1 tail. You get another head, tail. As it moves up and down, it's more heads or tails. You'll notice that this proportion is going back and forth quite a bit, a lot of variation. The second graph, 500 tosses, versus 20 tosses, a lot more tosses here, a lot of unpredictable behavior in this beginning here, and then it kind of approaches getting real close to that 0.5 towards the end. So a lot of variability in the beginning, and then after many flips, it becomes way more predictable at the end. It approaches that 0.5. So we're going to talk about the casino quite a bit in the probability chapter. One big money maker for casinos is the roulette table. It's a table where they spin a ball and you bet on what it's going to land on. There's numbers 0, double zero, and then 1 through 35. Half are black, half are red of those 1 through 35, then 0, double zero are green. And you have a bunch of different bets you could do. And what they do is they place this sign next to the table to try and trick people and think they have some kind of advantage. So somebody walks up here and says, "Oh, I see all these 19s. I know it's definitely not going to be a 19, or I'm due for a 20." They try and trick people into thinking that they're going to hit this next number, and they're giving the answers away. In actuality, the law of averages kind of tricks people into believing that because all these 19s just showed up, I'm not going to get a 19 for sure. And in reality, short-term, unpredictable behavior. You could get another 19 here, and it has nothing to do with any of the previous rolls here. They put this up here, for example, if this were all red for the past 10 numbers, someone might say, okay, I'm going to put all my money on my blacks. It's going to be a for sure thing. That's simply not true. A lot of unpredictability in the beginning, that short-term stretch. Long-term, yes, you're going to get some less 19s long-term because there's so many right here. But in the immediate short-term, the next roll of the ball, you're not guaranteed to get no 19. So just be careful of that law of averages type of thinking. On page 295, there's a situation where a couple, and you may have had a family member do this, aunt, uncle, parents, even grandparents, aren't we due for a boy? Plenty of families have had multiple children, and they keep having kids until they want the desired gender of a certain kid. So if they want a girl, they maybe try until they have a girl, they end up having a bunch of boys. Or the reverse happens, they want a boy and they have a bunch of girls. So families often have children until the desired sex of the child is had by the mother. But the big thing here is previous children have no effect on the next child. You might be thinking to yourself, well, it seems like it's really unlikely that you're going to have 6 boys and no girls. That's true. But if you think about the number of people that exist in the world and the number of pregnancies that happen every single day, there's going to be some very rare instances where you have all one gender. And it turns out they're actually not that rare when you consider the amount of people that we have on Earth. So if you're one of those couples that wants to have a certain gender baby, boy or girl, thinking that you have 3 or 4 the same in a row does not improve your chances by any means of getting that desired boy or girl. And the same, essentially, that law of averages thinking goes here with the roulette table sign. It does not help you in any way in the short term. Okay. You're going to be able to use a simulation to model chance behavior. It's a good tool even for complex situations where maybe the math is more difficult. Simulating it might be a little bit simpler, using Table D, using random integers, whatever you can get your hands on. So simulation, it's the imitation of chance behavior based on a model that accurately reflects the situation. It's called a simulation. So if you have some bigger situation that you want to run through, but you don't have, all those pieces, and you want to just boil it down to simple things like paper and a hat, where you're randomly drawing numbers out of a hat, cards out of a deck, random number generator and a calculator. You're simulating what's happening. It's less costly. It's mostly just free. Majority of the time, it just takes time to do, but it's real easy as well. There are 4 steps. First, state the question or ask a question of interest about some chance process. Plan. Describe how you use the chance device to imitate one repetition of the process. Tell what you will record at the end of each repetition. Do. Perform many repetitions of the simulation. And then conclude. Use the results of your simulation to answer the question of interest. So in the example here, at your high school, there are 350 students who drive to school. They are going to be raffling off 2 spots in the visitors' parking lot in the front of the school. Last year, 2 students won spots from the same AP class. Students were complaining that it was rigged. Design and carry out a simulation to decide whether it was plausible the lottery was carried out fairly. Remember that you need to provide a clear enough description of your simulation process for the reader to get the same results you did from only your written explanation. So be detailed. So first, state. Ask a question. So, is it plausible that the lottery was rigged? And plausible means, is there some kind of reasonable chance that it could be rigged? Not a guarantee, just reasonable chance. The plan. You can use lots of different tools here. We're going to use our random number generator and our calculators. So using the random integer function, we are going to generate 10 trials of choosing 2 students from a total of 350 students. Now, 10 trials means choosing 2. You're going to be generating 20 numbers out of your random number integer generator. So we're going to denote the number of students in the AP class, which was not mentioned here, but there are going to be 22 students in the AP class. So to make our lives easier, we're going to denote 001 to 022 as students in the AP class. And 023 to 350 are not in the AP class. So if 2 numbers are both from 001 to 022, then it is a successful trial. And if not, it's an unsuccessful trial. I went ahead and went through the process of doing this just to make the process go quicker here. Use the random integer function in our calculators to generate 20 numbers because we need 10 pairs of numbers. In the do part, I got the following pairs of numbers. 192, 239, 287, 139, 285, 001, 277, 253, 045, 097, and we have 095, 328, 226, 271, 138, 022, 011, 077, and then 172, 350. So if you look through all these trials, double check to make sure that you have any that have 2 numbers between 001 and 022. So this is going to be a no, an unsuccessful, unsuccessful, one of them successful but not the other one, so this is all together not successful, not successful, not successful, not successful. One is chosen but the other one is not successful. One is, one's not successful, not successful. So we have 0 out of 10 successful trials. All right, the last part for simulations, you're going to conclude. I'll try and get some space in the next paper here to write. We're going to conclude. So only 10 trials yields 0 successes. I attempted 50 trials on my own. So with 50 trials, only 1 success was found. So it seems the event is highly unlikely. Therefore, it is plausible that the lottery was rigged. Now, that plausible statement, remember, does not mean a guarantee. I'm not saying the lottery was rigged, but the idea of it is plausible, or it's probable. It's reasonable to think so. There's some evidence to back that up. You would need more evidence, obviously, more simulations or other kind of mathematical conclusions to come up with. So, just to recap, probability is the proportion between 0 and 1. It describes a chance process, and the proportion comes from the outcome that would occur in a very long series of repetitions. So this definition focuses on the many, many times repeating the process over and again. What does it approach? What number does the probability approach? And that's diagrammed here. Short term, heads or tails flipping. Long term, you can see it really gets really close to 0.5. We talked about law of averages and how it's that false belief that the next thing coming up is going to be the exact opposite of what you see, or you see a trend happening when you actually have independent events. It's essentially using this idea in the wrong way. Even though this does approach 0.5, if you got a lot of heads in the beginning, you should get more tails later. That's true over a very long period of time, not the next spin of the roulette wheel. Same with boy-girl situations, or kids with the parents keep trying to have the same, or more and more kids to get the other gender they desire. Previous children do not have an effect on that next child, so they think law of averages might help them out, but in fact it has nothing to do with the next child that they have. Simulations, the big four state you're going to ask a question of interest about the chance process. Plan, describe how to use a chance device to imitate one repetition of the process. Perform many repetitions of the simulation, and then conclude, use the results of your simulation to answer the question of interest. That's important. You should be answering the initial question that you came up with. We ran through a simulation together, and we kind of talked about what that means. Is it plausible that this is, is it possible, essentially? Yes or no. That is not a guarantee of what actually happened.